Good morning, fellow mathematicians, welcome back to another video. By popular demand, we are going to do this integral using complex analysis today, contour integration and Cauchy's residue theorem. But attention, my boys, I'm not going to do it on the original integral because I wasn't able to do it. This x squared term just ruined everything every time I tried it so often. So at first we are going to introduce a new integral. We are going to call it I in terms of t. And we are going to define it as follows. So that's the integral from 0 to infinity of sine squared t times x over x squared plus 1 dx. And you should be familiar with that. If you have seen my other video, link to the video will be in the description. We are going to differentiate it at first. So that means I prime in terms of t is now equal to. We're going to differentiate it in terms of t using the Leibniz rule for integration. Link in the description. So the upper and lower bound are independent of t. That means we can interchange the integral sign and the differential. And now we can use a partial derivative on the integrand. So that means we have the integral from 0 to infinity of the partial derivative in terms of t of sine squared t times x over x squared plus 1 dx. Great thing, we can differentiate that. That's nice. So that's the integral from 0 to infinity of this differentiated is 2 times x times the sine t times x times the cosine t times x over x squared times x squared plus 1 dx. And this and that we cancel out. And also this right here is the double angle formula for the sine. So what we end up with at first is the integral from 0 to infinity of the sine 2t times x over x times x squared plus 1 dx. That should all seem familiar to you guys if you've seen the video from before. But we can work with this. We've got rid of this x squared term and also of the sine squared, so this is making things so much easier. And notice just one thing, if we let t equal to 1, right here we will end up with our original integral I. So that's nice. So in order for us to continue, we are going to define a complex valued function, and we are going to call it f in terms of z. What will it look like? Well, we are going to define it in the upper half of the complex plane by using a semicircle. So this is going to be e to the 2i times t times z in this case over z times z squared plus 1. Okay, great. So this is our complex valued function and we can work with this. How can we imagine this function in the complex plane? So let's draw a graph right here. So we have this semicircle in the upper half of the complex plane, and it goes from some radius minus r to r. So we have this curvy boy up here. We are going to call it gamma. And well, we have this line segment. But the thing is, we want to integrate this function from 0 to infinity later on. But there's a problem. If we plug in 0 into here, we would integrate over singularity because that would explode to infinity. We can't do that, so we have to take a little detour. So we are taking a little detour. Some small semicircle with a radius of epsilon. Epsilon is a really small number. And well, we are going to let it go to 0 later on. And that means this line segment goes from minus r to minus epsilon, and this line segment from epsilon to r. Because it's a semicircle, that means this line segment on the real number line is going to be just epsilon. Okay, great. So we can work with this. And this is also our contour, capital C. Great. So let's see what we can conclude for now. So, and also we are going to call this little semicircle, let's see, lambda for example. Okay, so that now means we have a contour integral of f in terms of z dz. But how does it look like? Well, first things first, we have this curvy boy, gamma, right here. So we have this integral over gamma. And also, we have this next segment from minus r to minus epsilon. So we have an integral from minus r to minus epsilon of, we are walking on the real number line. That means we can make this a real valued function. So we are just going to call it f of x dx Also we have this next curvy boy, this lambda integral. So we have the integral of lambda, okay, and also we have this little line segment from epsilon to r. Okay, so positive epsilon to r integral, and also we are walking on the real number line again, so that makes things easier. F of x dx. Okay, great. So this is our integral right now, and now we can proceed. Because we haven't really taken a look at the poles of this function. So what are poles? Poles are the places where our function would explode to infinity. How does this work? Well, if for example 0 would be down here, our function would explode to infinity. So we have a few poles. So our first pole is at z equals to 0, so that's the trivial case. So let's conclude. We have poles at, we have a singular pole at z equals to 0. But what else do we have? Let's split up our function a little bit. So we have f of z equals to e to the 2t times I times z over. Okay, now we have the z. But here's something you might notice. This one. What is this one? Well, this is just a minus I squared. So we can turn this a bit around, and now we have the difference of two squares. And now we can use some binomial formula to break this up into c plus I and then c minus I. Okay, great. That means we have another pole at minus I and positive I. I hope you see where this comes from. So we also have set 2 and 3. This was set 1, set 2 and 3 at plus minus I. Okay, great. So we have found out our poles and everything. And now we have to take a look at the residue. So what is the residue? Right now, we only have a residue at the point I, because this is the only real pole that lies in our contour. Okay, so let's conclude this. We have some residue when z is going to I of f of z. How does it look like? Well, we have a single pole, a pole of degree 1, which lies at I, so that's great. So we are getting rid of the derivative and the residue, so all we end up with is the limit as z approaches to I of z minus I times f of z. Okay, but what is f of z? F of z is just this function right here. Let's use this form because it makes things easier. So let's plug this in. So we have e to the 2i t times z over, and also we are going to assume that t is a positive value. I'm sorry I didn't say that in the beginning. To make things easier for us. Z minus I, Z plus I. And also this and that we cancel out. This makes things easier. If we plug in I into here, well, we end up with e to the minus 2 times t. Okay, great. So this is e to the minus 2 times t. First observation. And also if we plug in I into here, this is I and 2i. So this makes minus 2 over minus 2. Okay, nice thing. So we now know that our contour integral is equal to this chunk, and also it is going to be equal to 2 times pi times I times the sum of all residues, but our only residue is this right here. So let's conclude everything. We now know that we have a contour of f in terms of z dz. What is that? Well, this is 2 times pi times I, and also times 1 over minus 2 e to the 2t. This 2 and this 2 we cancel out, and all in all we have minus I times pi over e to the 2t. So that's the value of our contour integral right there. And it's equal to all this chunk. So now let's play around with all those expressions. This is our new integral right now. Everything nice and split up. I also left this graph right here. And now we want to introduce a little substitution. It would be absolutely astonishing if those had the same upper and lower bounds, so we can bring them together. How can we achieve that? Well, we could introduce a substitution. For example, we could say that we are letting x go to minus x. We are going to transform it. It's just a dummy variable. It doesn't matter what you call it. You can also call it minus u. It doesn't quite matter. So what would happen to all this stuff if we let this little transformation hold? So we have still our gamma, and also we have our lambda integral. And now, so minus r would become r in this case. So we have r and we have epsilon. Okay, nice and great. This right here would just become e to the 2 I t times x, but with a negative sign, because we are letting it go to minus x over. Okay, now we have minus x, and we have minus x squared would just be x squared plus 1. Okay, and also we have minus dx in this case. So minus dx. But you might notice this minus and this minus would cancel out. So that looks great. We nearly have this form right here. But how could we get exactly this form? Well, we could factor out a minus 1 on this right here to turn around the upper and lower bounds. So by making this into a negative sign, we end up with our upper and lower bounds that we desire. And now we can use the linearity of the integral and add those two together. So let's do this real quick. I'm going to write out everything. Epsilon to r, e to the 2 I t times x over x, x squared plus 1 dx. Okay, nice. Now let's add those two together. So now we have our integral and our next integral. And also we have positive the integral from epsilon to r of e to the 2 I t times x, negative e to the minus 2 I t times x over x, x squared plus 1 dx. So we have the same denominator, so we can easily bring them together. That's absolutely nice, because you might notice something. This right here nearly looks like our sine and exponential form. So remember, the sine of x is nothing else than e to the ix minus e to the minus ix over 2i. So all we really need to add to this whole thing is multiply numerator and denominator by 2 times I, multiplying it by 1. That won't change anything. So we are multiplying it by 2 times I, and also we need a 2 times I in the denominator. So this whole expression right here would be equal to the sine. So let's conclude everything. So we have our gamma integral and also our lambda integral, and also 2 times I times the integral from epsilon to r of, and now we have the sine of 2 times t times x over x, x squared plus 1 dx, and that's nice. So now we have our integral that we are pursuing times the factor of 2 times I. And we also need epsilon to approach 0, and we need r to go to infinity. And now let's take a look at the limits and see what happens in the limit process with those two integrals. Let's observe them. At first I want to take a look at this lambda right here. Okay, so how does our lambda integral even look like? Well, it's a curvy boy going from minus epsilon to epsilon. We are going in the counterclockwise direction. So it's a curvy boy going from minus epsilon to epsilon of our complex function. So that's e to the 2 I t times z over z, z squared plus 1 dz. But if we let epsilon approach 0, in this case we have an integral from 0 to 0, and that would just be 0. That's not nice. We want to transform it a bit. So we are going to introduce a new substitution. So let our z equal to some natural parameterization epsilon e to the I phi. That would also mean that dz is now equal to I times epsilon e to the I phi d phi. Okay, nice. So now we can plug everything in. Let's see what we get. So we end up with the integral from, what are our upper and lower bounds? If we plug in minus epsilon into here, we would end up with minus epsilon is equal to this chunk. So we can cancel out the epsilons. That means we need minus 1 to be equal to e to the I phi. So we need to find a certain value for phi. Well, if we choose pi for phi, that means we are getting our desired expression. So our integral goes from pi to, if we plug in epsilon into here, we need e to the I phi equal to 1. Well, this is just 0 in that case, if I'm correct. So this is going to be 0. It doesn't quite matter what the bounds are. Okay, so now we have e to the 2 I t times epsilon e to the I phi. That looks absolutely weird. And also we have e to the I phi, and also an epsilon right here, times epsilon squared e to the 2 I phi plus 1, and also we have this term right here, I times epsilon e to the I phi d phi. You might notice this and that will cancel out. And well, nice, we can bring this I to the front, and then we have done a lot of stuff. So this is I times the integral from pi to 0 of e to the 2it epsilon e to the I phi over epsilon squared e to the 2I phi plus 1 d phi. Great. And what would happen now if we let epsilon approach 0? Well, that term would go to 0, so that's nice. And also this would be e to the 0th power, so that's just a 1. So this integral goes to, as epsilon goes to 0, to I times the integral from pi to 0 of d phi. We can work with this, and that would equal to I minus I pi in that case. So that's nice. We've done this, and now we want to take a look at our gamma integral. So we want to study gamma now. But what exactly is gamma? Well, our gamma goes from r to minus r. So those are our upper and lower bounds. Oh, I can't speak English. Upper bounds from r to minus r of e to the 2I t times z over z squared plus 1 dz. And I would love to say that this thing goes to 0 because we can use Jordan's lemma, but in my less complex analysis video, one person complained about me just saying or using Jordan's lemma. It's called a lemma because it's a present to us. We can use it however we want. But if you're complaining about that, we are going to evaluate it using some substitution. If you want this, I'm doing this. Okay, great. So, what would happen if we would introduce another substitution? So now let our z be equal to r times e to the I phi. That would also mean that dz is nothing else than I times r e to the I phi d phi. So great thing, we can plug everything in. This is now the integral from, okay, upper and lower bound, same spiel as here, but this time it goes from 0 to pi of, okay, now we have e to the 2I t times r e to the I phi over, now we have r e to the I phi r squared e to the I phi, but with a 2 up here in the exponent, plus 1, and also we have this chunk, I times r e to the I phi d phi. Great. Once again, some stuff will cancel out, so that's great. We can bring this I to the front and see what we get. This is now equal to I times the integral from 0 to pi, what a great rhyme, e to the 2it r e to the I phi over r squared e to the 2 I phi plus 1 d phi. But wouldn't be too great if we would just let r approach infinity on here. That wouldn't go anywhere because of this stuff right here. So we are going to use some absolute values and see if we can find some approximations. We now want to take a look at what would happen if we apply absolute values to this thing. So let's do this. Let's apply absolute values to both sides. But now we have to use the triangle inequality to distribute the absolute value into everything. That means the direct path is shorter than some detour. That means we have the absolute value of I, which is just going to be 1. It's just how it is. And now the integral from 0 to pi of the absolute value of e to the 2it times r times e to the I phi over the absolute value of r squared e to the I phi with a 2 plus 1 d phi. Let's take a look at the denominator at first. So that's going to be quite easy. So our denominator, r squared e to the 2 I phi plus 1. There's a certain identity, it's called the reverse triangle inequality, that we are going to use now. But there's one condition we need to meet. We need to get a minus here. So how do we get a minus? We are going to turn this positive 1 into minus minus 1. And now we can use the reverse triangle inequality, which tells us that this is greater or equal to the absolute value of r squared e to the 2I phi minus the absolute value of minus 1. Okay, the absolute value of minus 1 is just going to be a 1. So that's nice. And also we can use the multiplicativity of the absolute value and turn this into two absolute values. r squared is going to be a positive value, so that's also nice. So we are getting rid of this absolute value here, and also, well, the absolute value of e to the I something when the something is real is just going to be 1. So that means we have the absolute value of r squared minus 1. But r squared is going to be so huge later on in the limiting process that this is going to be strictly positive. So that's a positive value. And now we can take the reciprocal on both sides and turn this inequality around to make it fit that inequality right here. So that also means that we have 1 over the absolute value of this chunk right here, doesn't matter what it is less or equal to 1 over r squared minus 1. Okay, great. And now we only have to deal with this right here. That's going to be a bit more complicated. No, not really. So it's the absolute value of e to the 2 it times r. But what is e to the I phi? Well, this is just the cosine of phi plus I times the sine of phi. So we have the cosine of phi plus I times the sine of phi. Great. Now we can distribute everything into everything, and also we have a positive sign right here, or negative sign later on, so we can split this exponential function up into 2 exponential functions. So we have, at first, the absolute value of e to the 2 I t times r times the cosine of phi, so that's nice. And also we have positive becomes negative because we have I squared right here, and e to the negative. And we have 2 times t times r times the sine of phi. Whew. Okay, that's quite some work. And now we can use the multiplicativity again of the absolute value and break this up. Once again, we are dealing with e to the I times something, and all the something right here is going to be real. That means this is going to be 1. So we got rid of that. And here's a crucial observation. So we want to find an estimation for this right here, an approximation. How can we do that? Well, I'm going to tell you that this is less or equal to 1. So at first you might notice this exponential function can't be negative. It just won't happen. It's a real valued function and it won't become negative. So that's the first thing. We are getting rid of this absolute value. And also remember that our phi is between 0 and pi. We are moving in the upper half of the complex plane. So that's nice. That also means if the sine is between 0 and pi, this is going to be the graph of the sine. And it's just going to get to be real value, not real values, positive values up here. So our sine will always be positive. That also means we are ending up with e to the negative something. And well, that's going to be less than 1. It's 1 over something, and r will approach huge numbers, so it's going to be less or equal to 1. Okay, great. So we found some upper and lower bounds for our approximation. So that now means we have the absolute value of this gamma integral is less or equal to, okay, now we have the integral from 0 to pi of, so the numerator is going to be less or equal to 1, and this right here is going to be less or equal, we have a d phi right here, r squared minus 1. Yeah. Okay, and now if we let r approach infinity, that is just going to be 1 over infinity, and that's going to be 0. So this whole thing goes to 0 as r approaches infinity. So we have found out all the values of our integral, and now we can plug everything in. Now imagine we are taking the limits on both sides. The limits won't really affect this right here, it's just a constant in terms of the limits, and we know that our gamma integral is going to be 0. So the first part is just going to be 0. And our next part, what was the next one? Well, we noticed that we are going to end up with minus I times pi in the limit as epsilon approaches 0. And also if we let epsilon approach 0 and r approach infinity, we would end up with this original integral I prime of t. So we have positive 2 times I prime in terms of t. So that's everything we have observed. The 0 doesn't affect us, so that's nice. We can bring this to the other side, and also all the i's would cancel out. So we are getting rid of that, and we are making a real valued function out of this whole chunk. So let's bring this to the other side and divide both sides by 2, and we are ending up with a expression for I prime of t. So I prime of t is now going to be equal to pi over 2 minus pi over 2 times e to the 2, e squared. Okay, nice, but don't forget, we want to go back to our original I in terms of t, or it would be even better if we would just get our original integral, the solution to our integral. So like I said before, I in terms of t equals to 1 is going to be our original integral I. But if we plug in 0 into our original integral, I in terms of t, we would get sine of 0 and this whole thing would vanish. So here's something we can do. We are now taking the integral from 0 to 1 of I prime in terms of t dt. And this is now going to be equal to I t equals to 1 minus I at t equals to 0. Well, this is going to be 0, and this is going to be the solution to our original integral I. Nice. And now we have the integral from 0 to 1 of pi over 2 minus pi over 2 e squared dt. Okay, great. Integrating this is quite easy. This thing right here is something times e to the minus 2, so that's really easy. So we have pi over 2 times t, and then minus and minus becomes positive, so positive pi over 4 times e squared, and well, from 0 to 1. If we plug in 1 into everything, we get pi over 2, and also positive pi over 4 e squared. Great. I forgot the t right here. I'm terribly sorry. That wouldn't make any sense otherwise. Same thing here, and same thing here. I'm sorry for that. We fixed this. And if we plug in 0 into here, that would just be 0, and this right here would be e to the 0th power. And don't forget, we have in the second part of the integration, so this is going to be pi over 4. And pi squared minus pi over 4 is just going to be pi over 4. Whew. And that's it, we've solved it. And I don't have much of a chalk left. There was quite some work, this is going to be a long video. And now I have to write a 9-page text for some seminar. So stupid. If you did enjoy this video, please like and subscribe and recommend me if you like. I hope you enjoyed it. I'm going to do more complex analysis soon. And well, if you want to support me a bit more, link to my Patreon will be in the description. And up until the next video, have a flammable day. See ya.